Welcome back to Math 104. Let's look more closely at the normal distribution and how it works. The first property we've actually already noted. It's that the graphs of normally distributed data are bell-shaped, and in particular they are symmetric with respect to the mean. The left side of the curve is a mirror image of the right side of the curve. The second point is that the precise shape of the distribution is determined entirely by the mean, that's mu, and the standard deviation, that's sigma. So if you look at these three curves, yellow, red, and blue, they all are centered at the same point. They're all centered at 0, that's this 0 down here. So they all have a mean of 0, mu equals 0 for all three of them. But what makes them different from one another is that they have different sigmas, different standard deviations. The yellow curve is more spread out. It has a high sigma. The blue curve is very clustered about the mean. It has a small value of sigma. Then you have this green curve here, which has a different value of mu altogether, and you'll notice a little bit of a different sigma. It has a slightly different shape than any of the others. The key idea is that all normal curves are essentially alike. In particular, we can look at this fantastic applet at the Interactive Math website. I have here a normal curve. If I shift the mean left or right, the curve retains its shape. It's just centered at a different value. If I change sigma, when I make sigma smaller, that makes the curve narrower. When I make sigma larger, that makes the curve more spread out. But here's the key point. Look at these vertical dashes. These are marking off numbers of standard deviations away from the mean. So 4 here is the mean. This vertical dashed line marks one standard deviation below the mean. This vertical dashed line marks one standard deviation above the mean. As I change the value of sigma, I'm changing the shape of the curve, but it's still true that approximately 68% of the area painted green here lives between the mu minus sigma marker, the mu minus 1 sigma lower boundary, and the mu plus 1 sigma upper boundary. No matter how I change the shape, it's still about 68% of the area that lives in this region. It's still about a 68% probability that if I randomly select one data point from whatever data set this comes from, that data point will live between this vertical dashed line and that vertical dashed line, somewhere in the middle here. Similarly, no matter how I transform this, it'll be the case that about 95% of the area under the curve, painted in green, lives between these two boundary markers, mu minus 2 sigma and mu plus 2 sigma. So in that sense, all normal curves are alike. Once you know mu and sigma, you really know everything about the curve. Finally, if the values of mu and sigma are known, then it's possible to answer any question of the following form. What is the probability that a randomly selected data point lies in the interval from A to B? So if I know that the mean is 4 and the standard deviation is 1.35, I can go and figure out what is the probability that a randomly selected data point lives between, say, 3.44 and 5.39. Once I know what mu and sigma are, I have enough information to figure out how much is this probability. What fraction of the overall area under the curve is painted in green here? How do we figure that out, knowing mu and sigma? We'll see that soon. To work our way up to it, let's understand the special case where mu equals 0 and sigma equals 1. So if data are normally distributed with mu equals 0 and sigma equals 1, then they have a standard normal distribution. Notice that the word data technically is plural. The idea is that if we can understand how to compute probabilities in the special case when mu equals 0 and sigma equals 1, then we will be able to make adjustments. We will learn how to make adjustments to compute probabilities for any mu and sigma. Here is a key example that arises often in real life of when mu equals 0. So what kind of data set would have some negative numbers, some positive numbers, but their average is 0? Consider a water bottling facility which produces 1-liter bottles. Due to imperfections in the bottling process, there will always be imperfections in any physical process, not every bottle contains exactly 1 liter. In each bottle there is typically some small error. Now suppose in this example that the errors have a standard normal distribution, which means that the errors are bell-shaped with a mean of 0 milliliters. So in our picture this is 0 milliliters. and a standard deviation of 1 milliliter. So this is 1 milliliter, 2 milliliters, -1, -2. That means that for a bottle of water to be 1 standard deviation below the mean, it is underfilled by 1 milliliter. To be 2 standard deviations above the mean means that it is overfilled by 2 standard deviations. So you can see how it would make sense that the average error would be 0. If you take all the errors, some of them are negative, some bottles are underfilled, others are overfilled, and the average of these amounts is 0. Having this example in mind, we would like to be able to answer questions such as the following. What is the probability that a randomly selected bottle is overfilled by 1 milliliter or less? In other words, it's overfilled, but the amount by which it's overfilled is 1 milliliter or less. So this is the same question as what percentage of bottles are overfilled, but overfilled by an amount of 1 milliliter or less? Another kind of question we'd like to be able to answer is what is the probability that a randomly selected bottle is overfilled by 1.75 milliliters or more? Now, this is a truly new kind of a question for us, because so far, we've only found probabilities involving whole numbers of standard deviations away from the mean. Now we have a non-integer number of standard deviations away from the mean, so we'll need to see how to handle this. In the special situation that mu equals 0 units and sigma equals 1 unit, there's a table in which we can look up the probability that a randomly selected data point falls within a specified range. You'll see this table in a moment. It's also available in the book and on Sakai, and can easily be found online. This table is called the standard normal curve table. An entry in the table we are about to look at is the probability that a data point from a normally distributed dataset lies in a region that looks like this blue region right here, between the mean and someplace away from the mean. A certain number of standard deviations away from the mean. This z is expressed as the number of standard deviations above the mean. If you ever see a negative value of z, it's referring to something below the mean. The shaded region in the picture is very important for understanding what the table entries signify. We're interested in a range of scores between the mean and some number z, and that z will tell us where to look inside the table to find the probability that we're looking for. Here's the table. Don't worry, you don't have to memorize it. But you do have to understand how it works and what its entries mean, and how to find the entries that you're looking for. The way this picture is drawn, z lives somewhere between 0 and 1. So these hash marks here are marking off number of standard deviations. So this is 2, this is 3, -1, -2. So this z right here lives somewhere between 0 and 1. From the way that it's drawn, let's say that z equals 0.83. The method we're about to learn applies when z equals anything, but let's work as an example with 0.83. These digits, going as far as the first decimal place, tell me what row to look in. So I should look in the 0.8 row. Then this second digit after the decimal point, that 3, is telling me to look in this column right here. So there's going to be a place where this column and this row intersect one another. There's going to be one entry in common between this row and this column, and that's the number that we're looking for. This 0.2967 right here, that means there is a 0.2967 probability that a randomly selected data point will live between 0 and 0.83 along the horizontal axis here. Another way to say it is that 29.67% of the area under this curve is shaded in blue here. Let's practice this. What is the probability that a randomly selected bottle is overfilled, but overfilled by an amount of 1 milliliter or less? It is strongly recommended before solving problems like this, involving the normal distribution, to draw a sketch first. This is exactly the region between the mean, 0, and 1 standard deviation above the mean. These are bottles which are overfilled, so we're shading in a region to the right of the mean, but the amount by which they're overfilled is 1 milliliter or less. We could have just asked the empirical rule about this. It would have told us 0.3413. But let's see how we get that from the table. Our z here is 1.0. We're inquiring about the region from 0 to 1.0. This table specifically knows about regions that start at 0 and go to somewhere. Since we're not given any more information, we should really think of this as 1.00 for purposes of looking up in the table. The 1.0 part tells me to look at row 1.0. The 0 for the second digit tells me to look at column 0 here. So notice how all the column headers here are of the form 0.0 something. This means that it's focusing on how much is that second digit past the decimal point. When the second digit past the decimal point is 0, as it is here, we look in this column, which is specifically for z values with a 0 as the second digit past the decimal point, and lo and behold, here is our probability, 0.3413. Isn't that great? It agrees with what the empirical rule said. So our answer is 0.3413. What is the probability that a randomly selected bottle is overfilled, but overfilled by an amount of 1 milliliter or less? 0.3413 is that probability, or 34.13% of the bottles are in this region overfilled, but overfilled by 1 milliliter or less. And now something the empirical rule did not directly tell us. What is the probability that a randomly selected bottle is overfilled by 1.75 milliliters or more? Let's be really careful. We've got 0, 1, 2 standard deviations. This 1.75 lives somewhere around here, so that's 1.75. And we're shading in a region that is above 1.75. Now this is where we have to be careful. This kind of region does not look like the kind of region that the table directly knows about. What the table knows about are regions that go from 0 up to a certain point. So let's think what it means when we look up z equals 1.75 in the table. The 1.7 tells me which row to look in. The 5 in the second decimal place tells me which column to look in. When I look to see where the row and the column meet one another, I find this number right here, 0.4599. Now let's be careful what this 0.4599 means. 0.4599 is the probability of a region that looks like this, of a region that goes from 0 up to 1.75. The probability that a bottle is overfilled by between 0 and 1.75. We need the probability that it's overfilled by more than 1.75. So this region here has a probability of 0.4599. It's really helpful to label this region with the probability when you draw the diagram. So this unshaded region, but which does correspond to what the table directly tells us. If this region has probability 0.4599, then our region that we care about has probability 0.5 minus 0.4599. Everything to the right of the mean has probability 0.5. That's exactly half the probability. Of the right half of the picture, we need to throw out part of it. The part we need to throw out has probability 0.4599, so what's left is 0.0401. This is the probability that a bottle is overfilled by 1.75 milliliters or more. It is a very common mistake to see the 1.55 milliliters, that is 1.75 standard deviations above the mean, simply look up that location in the table and find 0.4599, and then wrongly state that as the answer. You must do this subtraction to find the region that you're really looking for. Before going on to the next video, answer the following questions. What is the probability that a randomly selected bottle is overfilled by between 0.75 and 1.75 milliliters? I recommend drawing the sketch. This is a little bit thought-provoking, but you know enough to be able to do it. And then, what is the probability that a randomly selected bottle is underfilled by at most 0.25 milliliters or overfilled by at most 0.4 milliliters? Think carefully about this wording and exactly what region you need to draw here.